So let's continue studying some more properties of the Lebesgue outer measure. In this lecture we will look at two more properties. The first one is called finite additivity for separated sets, and the second one is called outer regularity. So let me start with a remark is that due to the Banach-Tarski paradox that we have seen before, due to the Banach-Tarski paradox, we cannot expect finite additivity property to hold for arbitrary subsets EF of Rd. This is to say that the outer measure of E union, so arbitrary disjoint subsets of Rd, which is to say that the outer measure of E union F may not be equal to the outer measure of E plus the outer measure of F. So this implies that we must restrict our attention to smaller classes of, rather than taking arbitrary sets E and F, we have to restrict what kind of sets we allow for considering finite additivity. So to smaller classes of disjoint pairs of sets E and F. So one such restriction is given by the so-called separated sets. So two subsets E and F of Rd are called separated if the distance between E and F is strictly greater than 0. This is the quantity given by the infimum of the Euclidean distance between 2 points such that x and y, such that x is in E and y is in F. So this infimum is strictly greater than 0. So in this case we call E and F separated. So of course if this happens, one can also show that this implies that E and F are disjoint, because if E and F have a common point, then the Euclidean distance between that point with itself is going to be 0, so the infimum will be 0. So separated implies disjoint. So the next lemma establishes finite additivity property for separated sets. So let E and F be subsets of Rd which are separated, be separated sets. Then we have the finite additivity property, which is that the outer measure of the union, Lebesgue outer measure of the union, is equal to the sum of the Lebesgue outer measures of E and F. So let's try to prove this. So by subadditivity, we have that the measure of the outer measure of the union is bounded above by the sum of the Lebesgue outer measures of E and F. So we have seen countable subadditivity. So in this case we only have only 2 sets, but we can add infinitely many, countably many empty sets, and then the measures for all the rest of the sets will be 0, and we will get this inequality. So countable subadditivity implies finite subadditivity. So it's enough to show the reverse inequality, which is that m star e plus m star f is less than or equal to m star e union f. So again notice that if m star e union f is plus infinity, then the inequality is trivial, inequality holds, and so suppose that m star e union f is finite. So now I am going to again use the infimum definition of the Lebesgue outer measure. So there exists, so given epsilon greater than 0, there exists a collection of boxes bi I equal to 1 to infinity, such that E is covered by the union of these bi's I equal to 1 to infinity, and the sum I equal to 1 to infinity of the measures of these bi's is bounded above by m star e plus epsilon. So now suppose that suppose that we have subcollections bi prime I equal to 1 to infinity and bj double prime. So to distinguish the indices, I will write here L for the first one and j for the second one, j equal to 1 to infinity, such that, so these are subcollections of the original collection, of the collection bi I equal to 1 to infinity. So each of these bl prime and bj double prime are one of these bi's. So such that E is covered by, I have to cover E union F by this rather than just E. I am going to cover E union F by the whole collection bi, and so now I am dividing the collection bi into 2 sub collections, one that covers E, so bl prime L equal to 1 to infinity, and F is covered by j equal to 1 to infinity bj double prime and we also suppose that none of the bl prime intersect F and none of the bj double prime intersects E. So then these two collections are separate, there is no overlap between them. So this implies that m star E plus m star F, this is bounded above by the sum L equal to 1 to infinity m of bl prime, and then j equal to 1 to infinity m of bj double prime. But if, because of this assumption that we have that none of the bl prime intersect f and none of the bj prime intersect e, this implies, due to our assumptions on these collections bl prime and bj double prime, j equal to 1 to infinity, we have that the sum I equal to 1 to infinity of the measures bi is equal to L equal to 1 to infinity m of bl prime plus j equal to 1 to infinity m of bj double prime. So this is because there is no overlap, overlap between these two collections bl prime and bj double prime. So this implies that the measure of outer measure of E plus the outer measure of F is bounded above by this sum MBI, but this was chosen such that this is less than or equal to M E union F plus epsilon, and since again epsilon is arbitrary, so we get the required inequality M star E plus M star F is less than or equal to M star E union F. But now in general, the assumption may not be true that none of the, so let me write it in symbols, BL prime intersection F is empty for all L greater than or equal to 1, and BJ double prime intersection E is empty for all J greater than or equal to 1. So this may not be true because, for example, if you have two sets E and F, so there could be one box Bj or Bi which intersects both, and so our assumption will be invalid because this set will neither belong to any of the BL primes nor will it belong to any of the BJ double primes. So this will violate our assumption. So this set violates this assumption. So what we have to do is to use the fact that these two sets are separated, and we have to break these big boxes Bi into smaller chunks so that none of the smaller bits overlap both, intersect both E and F. So note that each Bi can be partitioned into finitely many boxes. Now let me give it a different name, K equal to 1 to so Aki, K equal to 1 to Ni. So for each I we will have a partitioning of each box Bi into finitely many boxes such that the diameter of each Aki is less than or equal to R for any given R greater than 0. So here the diameter of a set A. This is the supremum of the Euclidean distance between any 2 points of A. So we can restrict the diameter of the partition boxes, the boxes used in the partitioning of each BI, such that the diameter is bounded above by any given positive number R. So if R is taken to be strictly less than the distance between E and F, then no AKI for I greater than or equal to 1 and 1 less than k less than or equal to Ni can intersect both E and F, so that the new countable collection of boxes AKI I equal to 1 to infinity, k equal to 1 to Ni. So this collection covers E union F, because the union, when you take the union of these AKIs over K, this is precisely BI, because this is a partitioning of this box BI, and this collection satisfies our assumption that there exist subcollections A. So rather than taking two indices, I can rewrite it, re-index it to write it as a collection n equal to 1 to infinity. So now we can break these this collection ANs into two subcollections, AM prime and let's say AQ double prime, Q equal to 1 to infinity, such that E is covered by the first collection and F is covered by the second collection, and it also satisfies that AM prime intersection F is empty for all M, and AQ double prime intersection E is empty for all Q. So this assumption will be satisfied once you subdivide each box BI into smaller boxes with diameter bounded above by the distance DEF. So note that this is a positive number, so R can be chosen here greater than 0. Okay, so this takes care of our assumption that we had before, and in the general case also we can reduce to that case. So this proves the lemma. The next lemma is called outer regularity, and this says that the outer measure, so let E be a subset of RD, then we have a formula for the outer measure given by the infimum of the outer measures of sets U that are supersets of E, such that each of these U's are open. So this is called outer regularity property for the Lebesgue outer measure, and this is one of the most important properties, and we will see that this property also can be it can also appear in the abstract measure space context. So let's try to prove this. So first note that m star e is less than or equal to m star u for any open set u that contains e. So we can take an infimum on the right hand side, and we will get m star e is less than or equal to the infimum of these sets u. Each of these u's are open, and e is contained in each of these open sets u. So this is obvious from the monotonicity property. Now, so it suffices to show the reverse inequality, which is that infimum over open sets of m star u is less than or equal to m star e. So in particular, what we will do is we will show that given epsilon greater than 0, we have infimum of these sets m star u is less than or equal to m star e plus epsilon. So again we use the epsilon trick, and we will try to show this inequality here. So to show this, first note that if m star e is infinite, then the inequality holds trivially. Equality holds. So suppose that m star e is finite. So in this case, this implies that there exists a collection of boxes bi I equal to 1 to infinity, such that E is contained inside this union of the bi's, and the sum I equal to 1 to infinity mbi is less than or equal to m star e plus epsilon. So let me take epsilon by 2 here. So now these bi's that we have taken, these may not be open, but we can enlarge each of these bi's as we have done in the last lecture. We can enlarge these bi's such that they become open, but still we can have control over the volume of the union. So for each I choose an open box vi prime such that the measure of bi prime, first of all, that bi is contained in bi prime, and the measure of bi prime is less than or equal to the measure of bi plus epsilon by 2 to the power I plus 1. So this implies that the sum for I equal to 1 to infinity m of bi prime is less than or equal to the sum I equal to 1 to infinity m bi, and then you will have an extra term of epsilon by 2, but this is less than or equal to m star e plus epsilon by 2 plus epsilon by 2. So these two epsilon by 2's can be written as epsilon. So we have produced E is covered by these boxes bi prime I equal to 1 to infinity, and so this is an open set. This is an open set, and the measure of the union of I equal to 1 to infinity bi prime is less than or equal to this sum I equal to 1 to infinity m bi prime, which is bounded above by m star e plus epsilon. So we have produced an open set such that it is bounded above by m star e plus epsilon. Therefore, when we take the infimum over all open sets, then it's going to be less than this quantity.